Yeah, good morning all of you dear friends. After a brilliant topic of magnetic induction due to current carrying conductor, as a brilliant topic it was, because we have a very good sense of finding directions, right? And that is why it happens to be a tough topic for just ordinary student who actually finds very difficult in using this right hand rule. Now next topic is a star topic. This time the topic is charged particle placed in magnetic field, and we'll continue this topic into 3 to 4 topics. First we begin with charged particle in magnetic field, single charged particle. Then we continue with large number of charged particles like current carrying conductor placed in magnetic field. Then we continue with the combination of conductors placed in a magnetic field. Then also we talk about a current loop placed in magnetic field. So likewise the concept will actually continue. And let us see the topic of charged particle in magnetic field. We have discussed charged particle in electric field in the concept of electrostatics. And when I am discussing about the charged particle in magnetic field, do have a comparative study, right? I will also do that. You also try to do that comparative study regarding any of the concept that we are now discussing. Now, charged particle, magnetic field, and I am using all the regular terms. Capital B, the magnetic induction of external uniform field. Mind it, here I am taking a uniform magnetic field. Q is charge of the particle placed in the magnetic field, I said, and the M is mass, V for velocity, and also another parameter such as angle, as we will now discuss. Now, charged particle in uniform field, the first point is stationary charges are not affected by magnetic field. Remember, whenever I am speaking about this concept, each and every statement is a solution for a question. It can be either a conceptual question or a numerical. Remember, every statement varies lots of importance. Stationary particle, stationary charge not affected in uniform magnetic field, whereas moving charges experience force. From these first two statements, what is that we infer? Why stationary charge is not affected and why moving charges are affected in external magnetic field? The answer is stationary charge is associated only with electric field, and electric field does not interact with magnetic field, whereas moving charge experiencing force in the magnetic field, the inference is moving charge is associated with magnetic field besides electric field also. So that is what is the consequence, and hence this magnetic field produced by the moving charge interacts with external magnetic field, and that is what is apparently seen as force acting on the particle. Remember, magnetic field versus magnetic field. Moving charge producing magnetic field, and that is why you remember one of the statements that we have given in the Coulombic force. Stationary charges, for only stationary charges, Coulombic force F equal to kq and q2 by r square is applicable, but not for moving charges. Why it is not applicable to moving charges can be a question in accession reasoning, and again the reasoning is, yes, moving charges are associated with the magnetic field also, and that is why now the force of interaction is different from that kq1 q2 by r square. We cannot evaluate. No. Moving charge experiences force, famous expression. This vector form I am writing, the force vector F bar is charge times a scalar, and look at this quantity V bar cross B bar, a cross product of vectors in which order very important. This is V bar cross B bar. Now in the scalar form I have written as QVB times sine theta. What is this theta refers to? theta refers to angle made by V bar vector with the B bar vector. It means the magnetic force on a charged particle depends on charge of the particle, velocity of the particle, external induction strength, and also angle between V bar and B bar vectors. And remember, this expression is independent of mass. So magnetic force on charged particle independent of mass. Similarly, even I have told you I have a comparative study. F equal to EQ is said, where the electric force is depending on charge only, independent of mass. The same way magnetic force on charge is also independent of mass. Now, one very important point regarding this magnetic force, that forces will be of different nature. Now you see we are writing it as cross product of V bar and B bar. V bar is a polar vector, a real vector. Magnetic induction is also a polar vector. Now this is the cross product of two polar vectors. Remember the property of cross products of vectors? The two polar vectors, when cross is taken, the resultant is always a pseudo vector. Now this F bar is a pseudo vector, and for all pseudo vectors we have to give direction by a convention, because the direction is not inherent for pseudo vector. They are always assigned, they possess assigned directions. Now here comes the rule to find the direction of magnetic force. This is the famous Fleming's left hand rule. In the Fleming's left hand rule, we are using three fingers: the thumb, the index finger, and the central finger, such that they are held perpendicular to one another. Three fingers of left hand, not right hand. Ampere's rule was for right hand. Look here, this is Fleming's left hand rule for magnetic force on charged particle. This is what is the rule. First one is the central finger. Central finger takes see the direction of current. Why it comes current here? Because current direction is always the direction in which positive charge moves, right? So the direction of positive motion of the positive charge is central finger. That is central finger, see, current. Central finger represents the direction of current. Index finger represents the direction of field. Index finger, take that I for induction. Direction of magnetic induction. If these two represent like that, then the thumb shows the direction of magnetic force. Thumb, T for thrust, thrust for force. That is how we remember. C, current. I, index, induction. T, thrust, the force. Like that we remember this. Now, in fact, I give you an alternate method. Using this may be sometimes difficult, and to make it easier and the same convention, I will give it as a right hand. Don't call it Fleming's right hand rule, but convention I am showing you. What is that? See, here it was the magnetic induction. Now here, all the four fingers of right hand I will show as magnetic field, magnetic induction. Earlier we said central finger represents the direction of current. Here I will take thumb in the direction of current, that is the direction in which a positive charge moves. Then the normal drawn to the palm represents the direction of magnetic force. Using this rule will be easier. I will show some of the examples where this one is easier. Applying rule to find the direction, it becomes easier, right? Index finger in the left hand, otherwise all the four fingers, see, like this. Now here this is what is current, and now here this is what is current. Now look, my thumb is upwards, so it says I direction of magnetic force. Now you can see the palm is facing upwards, the normal is upwards. Like that we get the same result. One more important point. So we have the magnitude and direction. Now another important point is that this force is only a deflecting force. Magnetic force on charged particle is a deflecting force. What is meant by that? It changes only the direction of velocity but not magnitude. Because a force can does two jobs. Either it can change the direction of magnitude, the direction of velocity, or magnitude of velocity, sometimes both also. Right? Now this force, the magnetic force on charged particle, does not cause any change in the magnitude of velocity. Only direction is changed, and hence it is I have taken as deflecting force. Speed remaining constant, velocity changes. Remember, velocity changes in terms of direction. Velocity changes and hence momentum changes and hence there is force. But other way, speed does not change. No change in speed means no change in kinetic energy. No change in kinetic energy means work done is zero. So magnetic force on charged particle, work done is always zero. Remember these three conditions: speed remaining change, velocity direction changing, no change in kinetic energy, work done zero, is also the characteristics of centripetal force that we have talked in the circular motion. Therefore, this magnetic force on charged particle is a deflecting force and it acts as centripetal force when the situation arises. Right. Now these are the few aspects about force, and let us come to the small discussion about understanding this one. F equal to QB sine theta. The direction is very important here, theta. Look at this. For theta equal to 0 or 180 degrees, sine theta happens to be 0. Sine 0. So force is 0. So what does it mean? Any charged particle projected along the magnetic field or anti-parallel to the magnetic field, not affected by the magnetic field, means it continues its straight line path with same velocity, not speed, I am telling you, same velocity, uniform velocity will continue. Therefore, there is a possibility that a charged particle can travel in straight line with uniform velocity in the magnetic field. Remember, because conceptual questions will be very tricky and all these statements are to be used there. So if theta equal to 0 or 180, no force. What does it mean? Whenever I take a parallel component of velocity of the particle with magnetic field, this V parallel component always causes the particle to have its straight line path. Now, theta equal to 90 degrees, this sine 90 maximum 1. So, force is maximum. QVB is the maximum deflecting force experienced by the charged particle. Just now we have mentioned that it satisfies all the conditions of centripetal force. Therefore, because of this F equal to QVB, particle changes its path. From because we have projected in a straight line, the path changes from straight line to circular. The path becomes circular. Now the question is whether it is only a part of the circle or full circle. We'll discuss that also. It all depends upon, yes, the space occupied by the magnetic field, how large it is or how small it is, like that. So the path is from straight line to circular. Now most important discussion is the characteristics of this circular path. Now, what is the force? We said magnetic force is QVB. And it provides necessary centripetal force, that is I am writing mv squared by r, if r is the radius of the circular path described by the charged particle. See, our no memory, because after this you will find some 3 to 4 or 5 different formulae, but we never try to memorize them. In fact, this is the basis. Afterwards, all the things you can do it in 5 seconds. Now, QVB is equal to mv squared by r. V, you have to cancel. You get r is equal to mv upon bq, right? R is equal to mv upon bq. This mv, mass times velocity, nothing but momentum. Momentum by dq. See, small p have taken. Momentum by dq. And very popular expression in physics. What is that? relation between kinetic energy and momentum, K equal to P squared upon 2m. Very popular relation. We use it quite often in all the 30 or 40 whatever chapters you say in physics. So K equal to P squared by 2m. Therefore here P I will write in terms of kinetic energy, under root you will get, right. So the same I am writing here. So this is under root 2km upon BQ. Don't feel that we have to memorize all this. This is a very simple momentum written in terms of kinetic energy. Now K here refers to the kinetic energy of the charged particle. Here again I will give you an expression, right? Because it's a very popular one. Now in the case of for a charged particle accelerated in electric field. Accelerated in electric field. Because how does a charged particle gains kinetic energy, attains kinetic energy, means when it is accelerated through electric field, then our definition says K is equal to V times Q, the kinetic energy acquired by a charged particle, accelerated through a potential difference of capital V. Remember, this V was a small v I have taken for velocity and this one is for potential. V times Q, potential difference times Q. Therefore, here I will write R is under root of 2 VQM by, right, it becomes B, because B squared, it becomes B squared, because everything I have brought under root, therefore it becomes B square and this becomes Q square VQ, right, VQ, one of the Q gets cancelled, therefore I will write it in the denominator B squared times Q. So all the different expressions you have for the radius, every expression is very very important for our NEET CET. Radius, we remember only this expression, radius equal to momentum by BQ, the other relations are like this. Yeah, now let us have our common sense discussion. I said this is common sense discussion because a regular procedure for any of the concept that you deal with. These are the expressions earlier we got, R equal to mv by bq. See, when we are talking about the radius of a particle and the changes in the radius of the particle for different data, see, data is important. How? Because here you see, now using this expression, I write for a given velocity. Supposing alpha particle proton projected into a magnetic field with same velocity, electron proton into same velocity, like that. So different particles and comparison when it comes, see, for a given velocity R proportional to m by q, m for mass and q. Generally this q by m refers to specific charge, right? Therefore it is R proportional to 1 by S. I call it if S is the specific charge of the particle. So comparison requires the data. Which of the data is given? Now you see here for a given momentum, same example, proton and alpha projected the same momentum, then it will be independent of mass. No mass term here, therefore it is R proportional to 1 by Q only. In such case, proton and electron, if you take, though masses are different, velocity same, but momentum same if it is said, then R proportional to 1 by Q, proton and electron same charge and therefore same radius, like that. R proportional to 1 by Q. Now here I don't write the ratios, you have to R1 by R2, Q1 by Q2, like that. Always when you are writing such ratio, make sure that 1 is for the initial values, given values, 2 for final values, that is required values. Now here you see for a given kinetic energy, particle kinetic energy given projected into the magnetic field, then it is R proportional to under root m by q. See, different relations we will observe, and that is why reading data is a very very important thing. Never take question for granted. Read the question thoroughly, fully, and always I am telling you keywords. The keywords should give you the solution. Now here R proportional to under root m by q. Another result. When do we use this result? Supposing two or three different particles presented in same electric field, they're accelerated under same potential difference. See here, what is that? R proportional to under root m by q. Like that. So comparison of radius requires. And one more thing you see here. Supposing the same expression, if I rewrite, this is what is that you get. Kinetic energy K is equal to B squared Q squared R squared by 2M. One more result. Supposing you are asked to calculate the kinetic energies, comparison of kinetic energies. What are the keywords? Charged particles. Yes. Traveling or projected in magnetic fields and the kinetic energy. Remember, this kinetic energy is a constant. Why? Magnetic force is only a deflecting force, no change in speed and no change in kinetic energy is our result. Now, same expression, you see R is mv by dq. R equal to mv by dq. Remember, these things only one expression but getting number of other expressions. Now we are talking about one more concept. What is that? R equal to mv by dq. Suppose if I take this as v by r is equal to dq by m. This v by r refers to angular velocity in the circular motion. It is called angular frequency. Omega is equal to dq by m. Therefore, frequency of revolution is dq upon 2 pi m. bq upon 2 pi m. If I take the reciprocal of that, that is the time period 2 pi m by bq. See, one more important result. No memory, the same expression R equal to mv by bq. Earlier we have seen, in the case of the characteristic like radius of the circular path traced by the charged particle, depends upon both the nature of the particle, that is mass, charge, it depends, and also depends upon the motional aspect such as velocity, momentum, kinetic energy. Now look at this expression. What is your take from this expression? You have B for external induction, Q and M are referring to the mass and charge of the particle. You don't find any as parameter or regarding motion here. So what does it mean? Frequency or time period is independent of motion, either velocity or momentum or kinetic energy. Depends only on nature of the particle, right? So for a given particle, whatever may be the changes in the velocity or energies, no change in frequency. Please do remember frequency, and that is why time period also, they are independent of motional aspects like velocities and this thing. So theta is equal to 90 degrees is a very, very popular case. So we have the expressions for the characteristics of the circle described by the charged particle. Now here let us take case 3 also. The third case we are discussing, like theta not equal to 90, theta not equal to 0. That is 0 degrees less than theta less than 90 degrees. In between 0 degrees and 90 degrees. Yes, what will be the result? Here, when it is the case, this velocity vector v bar has two components, which is a very regular case of resolving velocity. Now, one component becomes v parallel, the other component becomes v perpendicular. This is parallel to b bar and this one is perpendicular to b bar. Now remember, always angle with b bar we have taken, therefore v parallel will come as v cos theta component and this is v sin theta component. Now remember, go back, what was our discussion? For theta is equal to 0 degrees. Parallel component of velocity. Parallel component of velocity always tends to keep the particle in straight line. Whereas perpendicular component, just now we have seen, perpendicular component of velocity always tends to, yes, make the particle to move in a circle. So now there are now both the tendencies of straight line motion and circular motion, therefore it's a combination. As a combination, what we observe is that the path becomes, yes, this is what is a helical path, spiral path you can say, helix you can say, helical path it comes. For this case of in between 0 degrees and 90 degrees. And now, if I said 30 degrees or 120 degrees, it is one and the same. So do remember, if I said 0 between 0 degrees and 90 degrees and someone asked her what about 150 degrees or 130 degrees, whatever may be the case, other than 0 degrees and other than 90 degrees, this will be the case, the path is helical path. In this helical path also I write one characteristic, right? What is that? Right. This helical path, see this is what is one circle due to the perpendicular components, and whereas it will also be moving if suppose this is what is B bar, right? Now it is also having the straight line motion. So next circle it will become over here. This is what we call pitch of the helix. Pitch of the helix. Yes, the distance between successive circular paths is what is taken to be pitch. Now how to calculate pitch of the helix? Now very definition says that what is the pitch? Pitch is the displacement of the particle in its direction or in the direction of its motion. Therefore here no accelerations, remember, no accelerations due to the V parallel component, no accelerations, therefore pitch is nothing but displacement term. Displacement is equal to what do we write? Velocity times time. What velocity we have to consider here? Parallel component, which is V cos theta. This is V cos theta. And what about the time? Time here refers to time for this, which becomes nothing but time period, because during one circle it comes to this pitch, displacement. Therefore the time substitution is 2 pi m by bq. So V cos theta times 2 pi m by bq. This will give us the pitch of the helix. So charged particle in magnetic field, starting from force and then the characteristics of that force, afterwards the different cases of theta versus theta, that is angle between V bar and V bar, all the possible cases. As I have to do, each and every statement that we have given is a solution. Hope you practice it well. Now let us try to draw parallels between two forces. The magnetic force on charged particle versus electric force on charged particle. Remember, in both the cases I have considered uniform magnetic field or uniform electric field. That is sufficient for our NEET and CET. Now the only similarity between these two forces are, both the forces are independent of mass. In the case of electric force, you write F equal to EQ, independent of mass. Whereas in the case of magnetic force, we write F equal to Q VB sin theta, again independent of mass, like that. Remember, only force is independent of mass but not acceleration, because when we write acceleration, A is equal to F by m. Therefore again we will find that A proportional to 1 by m relation valid here, right? So this is only similarity with respect to the independent of mass, but all the other striking differences between the two here I have just listed out. First one is the magnetic force on a charged particle, right? It's a pseudo force because we have told that cross product V bar cross B bar, two polar vectors cross giving rise to pseudo vector, whereas this electric force is a real force. Next, magnetic force on the charged particle, right? This QB sin theta is only a deflecting force, no change in kinetic energy, only change of direction. But here it changes both magnitude and also direction. Remember, charged particle moving in an electric field, no question of without any change. It will definitely change, at least magnitude will change. At least magnitude will change or both will change, right? And actually we will discuss another case also. Now we are talking only about charged particle, uniform magnetic field, charged particle, uniform electric field. There is another possibility also in non-uniform electric field charge. What happens? We'll have another discussion, but here comparison I am taking only uniform field. Therefore, it is only deflecting force here changes in both magnitude and direction. Therefore, when a charged particle is in electric field, no question of uniform velocity. No question of uniform velocity. Whereas, for the magnetic force, straight line with uniform velocity is possible in magnetic field. When we have told the case of theta equal to 0 degrees or 180 degrees. What happened? No deflecting force, continued the straight line path with the same velocity, right? So uniform velocity is possible in the case of Fm, but not possible in the case of Fe, the electric force. And one more thing I want to tell you that here, whenever charged particle magnetic field is given, there are only two possibilities for the path of the particle. It is either straight line with uniform velocity for the case of theta equal to 0 or 180 degrees, or else the other possible path is of course circular path for theta equal to 90 degrees. Other than these two, also we have told the other path is what is helix, right? Helix is also possible path for any angle other than 0 degrees or 90 degrees. This is what is. But here, in the case of electric force on a charged particle, there are again two possibilities such that first possibility is straight line with acceleration. Straight line with uniform velocity not possible in the case of electric field. Straight line with acceleration will always be there, and next possibility is that the path is parabola. There is no question of circular path in the case of a charged particle in uniform electric field. Such circular path for a charged particle is possible in the case of non-uniform electric field, but in the case of uniform electric field, the only possibilities of the path that you can get is either straight line with acceleration or parabola. So this comparison is also very important. Please do remember. Now we will continue that. I have told you firstly consider a charged particle moving in straight line experiencing magnetic force. Now we extend this idea. We have now placed a current carrying straight conductor to be simple. Current carrying straight conductor placed in an external uniform magnetic field. Now what do we mean by current? Since it carries current means we know by the principles of current electricity that large number of free electrons are now flowing inside the conductor. Now each and every moving electron, what is that velocity? We talked about that as a drift velocity. You remember? Drift velocity J is equal to drift velocity V is equal to J by Nu. We had a relation, right? So now each and every electron is moving inside the conductor, and for which this magnetic field will act, and therefore each and every moving electron, not electron I have told, each and every moving electron will experience a force. Now the aggregate of the forces on all those electrons, large number of electrons are now flowing, the aggregate of the forces on all those electrons apparently I'm underlining this point, apparently will be seen as force acting on the conductor. In fact, it is the force acting on the electrons that are flowing inside, and apparently will be seen as force on this conductor, and F is equal to I times L bar cross B bar is again the expression for the magnetic force on the current carrying conductor. Symbols with regular meaning: I, current carried by the conductor, L, length of the conductor, and of course B bar, the external induction. The magnitude I am writing in the scalar form. F is I, L, B sin theta. Again the same cases will arise: theta equal to 0 degrees, 180 degrees, F equal to 0 and theta equal to 90 degrees maximum. All such cases we will also discuss. And since it is the extension of F equal to QVB sin theta, the direction of ILB sin theta force is also same rule as given by left hand rule, right? See, direction of current, induction by the index finger, then thumb shows the direction of magnetic force. We'll do some examples where I will use my right hand and give you some solutions. Instead of this also, I have told you we can use the same right hand convention also. F is equal to ILB sin theta. Using this, we have one very important concept as force between parallel conductors. Remember this concept? Force between parallel conductors. Force between parallel conductors. Here I consider, yes, two conductors P and Q placed parallel to each other, and I am writing as R the parallel distance between them, and they now carry currents. Let those currents be I1 and I2. These currents can be either parallel, that is in the same direction, or anti-parallel currents, right? So two possibilities are there, we will discuss that. Now in this case what happens? This is a straight conductor carrying current, and according to the Einstein experiment principles, it will produce a magnetic field around it. So now P is a current carrying conductor, produces magnetic field. In that magnetic field, Q is another current carrying conductor. Now by this expression, field is produced by P, current is carried by Q. Therefore, this conductor Q will experience a force. Let us see what is the direction and all. Similarly, Q also produces a magnetic field around it, and in that field P is a current carrying conductor. Therefore, P also experiences magnetic force. Natural, it becomes action reaction pair. F12, F21, like that action reaction pairs will appear now. Now what is that force we are now writing? When I am writing, look at this expression carefully. Now force on P by length of P equal to force on Q upon length of Q. This is now, we are not writing the total force acting on the conductor. We are writing an expression for force acting per unit length, and that will be same. Because here you see, supposing these are of different lengths, then always remember the one with higher length will experience more force. That is what is the idea here. So we are now writing force per unit length, which is same for both, and which will be the famous expression mu naught I1 I2, the currents carried by them on the denominator is 2 pi r. 2 pi r, again force depending upon the currents, directly proportional, and it depends upon the distance. Inverse relation you will observe, right? Now what about the direction? Now the direction, again we use left hand rule. We did that in detail in the classroom. So once again, class notebook will help you. Here I just give the statement that for I1 and I2 parallel, I1 and I2 parallel, both are parallel and of course carrying current in the same direction. I1 I2 parallel, the force will be towards each other. So it is like P and Q attract each other. Apparently it appears. So I1 and I2 parallel means attractive force. It is attractive force. Now I1 and I2 anti-parallel, yes, that will be the case of repulsion. P and Q repel each other will be the case. But generally, what do we mean by attraction or repulsion? We have discussed in the classroom. Hope you remember. Attraction means anything moving from weaker region to stronger region. We call it as attraction. In the case of field concept, what is attraction? Yes, it is from lesser intensity to higher intensity. If that tendency is there, it is attraction. Otherwise, from higher intensity to lesser intensity is always taken to be a kind of repulsion. So that is what is taken here. Now, this is parallel or anti-parallel. Current direction is very important when we are doing examples. Suppose we are given not 2 but we are given 3 parallel or 4 parallel, and we are asked to find about a particular conductor, what happens to it. So like that, even there is a possibility of dynamical equilibrium and all, which we will do as solve as some simple examples in our next session. Same example of parallel conductors. is also given in the other way. How? This time it is not given as P and Q straight conductors carrying current. Rather they say this is a beam of charge. Q is a charged particle and such a large number of particles are flowing. This is a beam of charge. I write it as Q1. This is also another, yes, beam of charge. Let me take it as Q2. So this Q1, Q2 equal or non-equal, like, unlike, different possibilities will all arise. Now you will go through that. And again same, these parallel beams at a distance are. Then what happens? Now this beam of charges also nothing but a kind of current only. Suppose this is a beam of charge where we have taken the velocity as V1. This is a beam of charge with velocity V2. So in this case also, earlier it was the case of two conductors carrying current. Now here also charge beam, charges in flow also gives rise to the same current carrying conductors, and in this case the expression will be F is equal to mu naught Q1 Q2 V1 V2 upon R rise 4 F proportional 1 by R rise 4 F proportional to V1 V2. All important results will find. If examples are created from this, they become very, very tough, and that is why I ask you to go through this. And now here, what about the direction, whether it is attractive force or repulsive force? Remember, we have told the direction of current means always the direction in which positive charge moves, we told. And in this case, earlier we have told parallel currents attraction, anti-parallel currents repulsion, right? If we combine those two concepts, the direction of current and also earlier example of attraction or repulsion, if we combine both, now this is what is I am telling you. See, what is that? Q1 and Q2, suppose like charges. Q1 and Q2 like charges, then if V1 bar parallel to V2 bar, it will be the same case of conductors, parallel currents, and parallel currents will attract. Again I am telling you, Q1 and Q2 are like charges and V1 bar parallel to V2 bar, therefore this will give the case of attraction. This will give the case of attraction, and obviously naturally V1 bar opposite to V2 bar we will get it as repulsion. Now this is the case of what I have told, Q1 and Q2 both being like. Supposing if it is Q1 and Q2 unlike, then it will be reverse of that. What is that? Yes, Q1 and Q2 unlike, because remember the direction of current and none, and then whether parallel currents or anti-parallel currents. Combined, what we observe is that Q1, Q2 unlike, V1 bar parallel to V2 bar, now this will give rise to repulsion, and V1 bar opposite to V2 bar will give the case of attraction, like that. So here it can be beam of protons both, or one beam proton and another beam that of electron. Proton beam, alpha beam, electron beam, alpha beam, any such beam. And most important point is, please look for these arrows, V1 bar, V2 bar, parallel or anti-parallel is vital in our answer. Now let us see the case of current loop in magnetic field, uniform magnetic field. Now, in fact, this figure itself is a very important thing I tell you, because even there can be questions based on this figure. How? See, this is a uniform magnetic field of induction B, where I have shown a coil, and for simplicity or for simple mathematical simplicity, I have taken it in the form of a rectangle. Now after that, whatever result we get, it can be used for any other geometry, right? Remember, maybe now we have shown the case of a rectangle rectangular frame, rectangular loop, whatever result we get, it is applicable for any other geometry also. Now in this example or in this figure, what I have shown is that the plane of the magnetic field is plane of the board, right? Plane of the board happens to be the plane of the magnetic field, and supposing if I take this as the loop, now the loop is placed like this, that is plane of the magnetic field coincides with the plane of the loop. Otherwise I will say plane of the loop coincides with the plane of the magnetic field. That is how it is initially placed and taken. It need not be always the same case, but it can also be supposing if the planes are making some angle, they can be in such case also. So for both cases, first I discussed about the conceptual thing. Now for this case, what happens? Force on QR equal to force on SP is equal to 0. Because for this, you can take it as 4 straight conductors case. And because of this theta is equal to 0 degrees for QR and SPF equal to ILB sin theta concept, sin 0, 0. Therefore now here is 0. Now this is the case we have discussed when the coil of the loop coincides with the plane of the loop coincides with the plane of the magnetic field. Supposing if it is not, then what happens? This is possibility for the given geometry, for the given placement or orientation. For any other orientation, if the planes are not coinciding, I am writing if planes does not coincide. Planes does not coincide, what happens means F, Q, R not equal to F, SP and it is not equal to 0. Number one. Second point is that these FQR and FSP will act as equal, opposite along the same line of action. This is what happens. So both are non-zero but act on same line of action. Same line of action means net force is 0, right? So though 0 or non-zero, they don't give rise to net force for both of them is 0. Now the other case, what is that? FPQ is equal to magnitude I am writing. FPQ magnitude is equal to the force on or as the 2 straight conductors. The case of theta equal to 90 degrees, F equal to ILB sin theta, theta 90 degrees force maximum ILB. Now, if you use the Fleming's left hand rule here in this case, what happens? This is the force on PQ which will be acting, yes, this way. Because if you use your left hand rule, see current direction. Let me show that. First direction of magnetic field, yes, index finger. Then current direction P to Q. Now I am taking the P to Q upward. Now look at my thumb. Thumb is inwards. So this is the force acting into the board, and whereas an RS you will get it as a force outwards. So here they are equal, therefore net force is 0. Since net force is 0, no question of any translatory motion, right? So a current loop placed in external uniform magnetic field, no translatory motion. But now look here, these two are equal, opposite, along different lines of action. How? Because if this is what is one force into the plane of the board, the other is towards you, outward force you get. Therefore, these are two forces, equal, opposite, and along different lines of action. Brush up, such force, such pair is what is called as couple. So they form couple. And whenever there is couple will act, torque. Couple will always give rise to torque, and torque gives rise to rotatory motion. Therefore, no question of translatory motion. Now the loop will experience rotatory motion. Now what is this expression for torque I am writing? So this torque is equal to I A B sin theta. Tau is equal to IAB sin theta for loop I am writing. That is a conductor bent in the form of some geometry. This I for current carried by the loop, A cross section of the loop, A for cross section of the loop, and that is what I have told you. Whatever may be the geometry, for our mathematical comfort we have taken a case of a rectangular geometry and we got an answer. Same is the case for any other geometry. Supposing if it is a circular coil or if it is called triangle, whatever it is. A for area of cross section, B for external induction, which we have taken a uniform. Of course, most important thing is about theta here. What is theta? Now here, this is in fact I into, this is A bar cross B bar. Aerial vector I am taking, which is a pseudo vector. A bar cross B bar is the thing. See here. Now here, understanding the theta is very, very important in this case. There are two vectors, A bar vector. Many times you are told that aerial vector is a pseudo vector which is always given by outward normal. So this is aerial vector. If this is what is the plane of the loop, or else if we call coil, this is what is the plane of the coil and it is normal. This is A bar vector and this is what is B bar vector. Blue I am taking, this blue tip represents the magnetic induction. Now this is what is the angle between the blue marker and this black marker. Remember, the theta is not angle made by the plane of the coil with magnetic field. No. Remember, theta is the angle made by normal to the plane with B bar. In some cases, it will be given straight data as angle made by the plane with B bar. Then we will have a small change in the result. So theta definition, wherever it comes, very important. Angle made by B bar, not with plane of the coil, but angle made by A bar with normal to the plane of the loop or coil. Loop or coil, that is what it is. Therefore, this sin theta I will use for the case of angle. Supposing the same expression, I will write tau is equal to IAB, I will write it as cos alpha. When angle is made by B bar vector with plane of the loop or plane of the coil, then we will use cos alpha. So without any confusion, we should make use of this theta or alpha case. Now supposing in the case of that, a loop is replaced by a coil. Even last time also we did such examples where what is the difference between loop and coil? Coil is also loop made up of more number of turns. Therefore, if it is a coil, then what we do is tau is equal to NIAB sin theta or else NIAB cos alpha. Here this N refers to current as a total number of turns. Because earlier small n was used the number of turns per unit length with that sense. Here we are using coil and n refers to total number of turns, current carried by the coil, area of cross section of the coil, B external induction, theta angle made by B bar with normal to the plane. Now in this we will take this NIA. Remember last time we have told for a coil, when carries current produces magnetic field. Therefore, it acts as a magnetic shell, a dipole, and hence dipole moment. What was the expression for dipole moment? It is current times cross section for a conductor. If it is coil, we have multiplied that with the number of turns also. Same expression you will find here, IA, and it is N. Therefore, this is nothing but, yes, this is what is moment vector M bar. This is what is moment vector M bar, and this vector is B bar. Tau bar is equal to M bar cross B bar. Same result as that we see for a magnetic dipole in external field, like that. So this expression is very, very important. Keywords are current loop, magnetic field, torque, and these are the different parameters that are now related. Though today's topics were like a continuity. It began with a single charge in a magnetic field, then extended with the current carrying conductor, then more number of conductors, and then we continue with this loop. Make sure you are ready with all these concepts so that in our next session we'll solve good number of examples. And also one more reminder, every time I'm telling you, on everyday basis you are getting the assignments. Please go through those assignments. And I tell you what, anybody who after brushing off these concepts, do your assignments, 50 marks in CET is guaranteed. Out of 60, anybody can do 50. In the classroom also I have told you, our classroom notebook, our classroom tests and these assignments, if you are ready with 60 on 60 is very much easy, very much possible in the case of CET. NEET also you can easily solve 30 questions. So with this again I am telling you, please go through all your assignments and meet or call your teachers for any of your doubts clarification. Have a good day.